Hi, everybody. Let's jump into our next section. We're going to be talking about 4.1 maximum and minimum values. Turns out 4.1 and 4.3 go together, but okay, what's 4.1 all about? Maximum and minimum. So turns out we'll be able to identify where maximum and minimums happen on a graph or on a function without seeing the graph, just based completely on derivatives. So to begin, we want to define the two types of maximum and minimum. There's an absolute maximum or absolute minimum. Those kind of, probably the name suggests what that is. The absolute means that they're either the very highest or the very lowest y value on the entire function. So look at the entire thing. What's the very highest y value? What's the very lowest y value? That's your absolute max or absolute min. But there are also local maximums and minimums, or sometimes you hear those called relative maximums and minimums. A local max or min is the highest or lowest point just in a small neighborhood of the function. So by neighborhood, we're sort of referring to really just looking at the points that are nearby. Maybe it's the highest of those, or it's the lowest, maybe not on the entire function, but just kind of locally, you might say. So just a quick example here to give us a picture. So created this graph really fast and sort of labeled some of the interesting points on that function. Let's talk about what's the absolute max, absolute min, local maxes, local mins. So looking right there, let's start with the absolute max, right? So we say, okay, well, that'd be the highest y value on the entire thing. Say, well, I mean, right there, that point, the highest point is at 3, 7. And so we'll say y equals 7 is the absolute max, the very highest y value. How about the absolute min? And now this one can be tricky for a moment. So we notice that there is a point down here. The lowest point that's labeled is at 5, 1. However, kind of toward the right, the function is dropping down further than that and even has an arrow indicating that it's dropping and dropping and dropping to negative infinity. So it turns out here, there is no absolute min. There is no smallest y value on this function because, if it keeps going down and down and down forever, well, I guess it kind of explains itself. There is no smallest y value. You might think, well, should we answer negative infinity? And no, we shouldn't. We should just say there is no, we need a specific value. And so if it does drop to negative infinity, let's say here, then there is no lowest y value. We'll just say none. How about a local max? Now, for absolute max or min, right, there can be only one. At most, maybe there's none. But for local, there could be several. So local maxes, there are actually two. The one at 3, 7 is a local max, but also the one at 8, 4. Right? If we just look in a little neighborhood, it's not the highest one on the whole thing, but just compared to the points nearby it, 8, 4 is a local max as well. So we're going to list them both, and notice that for the local max or min, we give the full point. So we'll say 3, 7 and 8, 4, where for an absolute max, we just give the y value. Now, as far as our work goes, if people want to list the full point when it comes to an absolute max, if you wanted to answer the absolute max is at 3, 7, no big deal. You're giving more information than what's needed. Technically, it's only a y value, but definitely for those locals, we want to know what x values those occur at as well. So give the full point. How about a local min? Are there any local mins? And yes, 5, 1 is a local min. So that'll be in the list. Now you might think, hey, what about 2, 3? Is 2, 3 a local min? I mean, it's smaller, the smallest point compared to the, kind of in its neighborhood. Turns out though, we don't want to list 2, 3 as a local min. That's not real clear why we're not doing that yet. The only local min here we'll say is 5, 1. Endpoints. So 2, 3 is an endpoint of the function, right? The function does not continue past that. It's like the function begins right there. So we consider that an endpoint. An endpoint could be an absolute max or min. Obviously, it's not either of those here, but there are definitely cases where an endpoint could serve as your local max or your local min. But we never consider endpoints as being a local max or min. And again, that doesn't really seem all that clear why. We'll get there, if not in this section, in the next one. And the answer comes down to, it has to do with derivatives and what's happening with the derivative at endpoints versus other local maxes and mins. So definitely some nuances, right? Like endpoints we'll consider absolute, but not local. Technically absolutes are just Y values, where locals are the full point. So trying to kind of get comfortable with those ideas. Okay, let's move along. We're going to start talking about local maximums and minimums for a little while. We'll come back to absolute maximums and minimums at the end of this section. So what can we say about, like, if we wanted to figure out where a function has a local max or a local min? So what's going to be really helpful is Fermat's theorem. Fermat, he made a lot of contributions to math. Didn't make a lot of contributions necessarily to calculus, but to other disciplines in math. Fermat is best known for Fermat's last theorem, which was actually, that theorem was around a couple of hundred years until it was proven. Fairly simple too, if you check out Fermat's last theorem. All he says is that there are no real solutions to this. Essentially, I'm kind of like, how do I phrase it? It's essentially the Pythagorean theorem, right? A squared plus b squared equals c squared. But for other powers. So anything higher than a power of 2. So like a cubed plus b cubed equals c cubed. He said there are no integer, there are no integer solutions for a, b, and c that will solve anything higher than the squares. So a squared plus b squared equals c squared, right? We've got 3 squared plus 4 squared equals 5 squared, right? There are integers that will make that happen. But for the cubes or anything higher, he claimed that there were no integers that would make that true. So like a to the 4th plus b to the 4th equals c to the 4th. There are no integers for a, b, and c that will make that happen. For any power 3 or above, for the equivalent of the Pythagorean theorem. And what's kind of interesting, he was kind of an interesting guy, kind of quirky, and he ended up just making that as a note in some of his writings, sort of in the margins, and it became this very famous theorem. And it seems pretty simple, right? A cubed plus b cubed equals c cubed. If you can find integers that would make that work, you would disprove him. Or if it was true, like, it shouldn't be all that hard to prove. For people who are operating at, the highest levels of math. But it turned out that it took over 200 years for somebody to prove that. It wasn't proven even until the 1990s. So, certainly within my lifetime, maybe in the lifetime of some of you guys. So anyway, then I'm kind of going off on something there, but that's Fermat's last theorem and why he's so famous. But he also came up with this, which we simply call Fermat's theorem in our course. If f of x has a local max or min at c, then f prime of c equals 0, or f prime of c does not exist. Okay, so we're saying if there is a local max or a local min, then either the derivative will be 0 there, or the derivative will not exist there. Let's take a look at some drawings, and hopefully we can make sense of this pretty quickly. So I'll just kind of, here's basically the last image that we had without labeling the points this time. And so we can see, yeah, there were local maxes, you know, at these two locations, and there was a local min here. And yep, I mean, at each one of those, there would be a horizontal tangent line. And so f prime of c would equal 0 for each one of those local maxes and the local min. Okay, so if there is a local max, then we know one possibility is your derivative there might equal 0. What about a derivative not existing? Well, that could happen at a cusp. So maybe consider this. So maybe there's a cusp happening, right? So right at that point, we can tell, hey, that's definitely a local max. It's the highest point, you know, considering like a small neighborhood around that point, clearly. But the derivative won't exist there. So it couldn't equal 0, but it would be D and E. So we have to consider that as a possibility as well. Okay, so thinking about these, we want to be real careful the way that we read this theorem. So we're saying if there's a local max or a local min, then we know either the derivative would have been 0 or not exist. This theorem does not work the other direction. So let me show you some examples of when we could have a derivative equaling 0, or we could even have a derivative D and E, but yet not have a local max or a local min. And we'll kind of see what that implies and where we go from there. Consider this down here. So we've got this function that kind of does this curve. This is actually my best attempt at drawing x cubed. So for x cubed, notice that at the origin, the derivative equals 0. So the function comes up, and just for one instant, right there at the origin, that it levels off and the tangent line is actually horizontal just for a moment, and then the tangent line would go back to being positive. So for f of x equals x cubed, f prime of 0 would equal 0. The derivative at the origin would be 0, yet that's not a local max or a local min. So it is possible to have a derivative equal 0, yet not be a local max or a local min. So even though if we have one, it could very well be that the derivative is 0. You could also have places where the derivative is 0. That's not a max or min, is the point. Okay. How about the D and E case? Sure, that could happen too. What if there was a cusp like this? Right, so instead of bending back, going up and then bending back down, what if it just kept going up? So there's this straight line, and then you hit a cusp, but then you just keep going up again at a different angle, right? That can totally happen. So your derivative would be D and E, yet that point right there is not a local max or a local min. Okay, so what does that tell us? What we're going to do is define the critical number. A critical number is an x value where either f prime of x equals 0 or f prime of x does not exist. Right, so we know that those are important x values. What are all the x values where either my derivative equals 0 or my derivative does not exist? Now, when we find critical numbers, we're really on the right track to locating where any local maxes or mins would occur. And you see that statement there, local maximums or minimums occur only at critical numbers. However, critical numbers might also contain points that are not local maxes and mins, as we saw in the last couple of drawings. So if I just jump back really quick, right, like in this first drawing, all of these C's, these would all be critical numbers because the derivative is 0. This would be critical. Here, this would be a critical number. And this would be a critical number. So if you get kind of the idea is we'll get a list of all the critical numbers for a certain function. And we would know that any local maximums or minimums that occur would have to be among that list of X values. Now that list might contain other points that aren't local maxes or mins. That's okay. This is where we're going to start to our investigation. All right, in the next video, we'll look at some examples. We'll look at these two functions here. Let's stop this video now, pick it up with those.